Bridge Preservation with Pre-stressed FRP Composite Materials by David White with the Sika Corporation.
Thank you, David, and good afternoon, everyone. Thank you to National Bridge Preservation for the time to present some new technologies in bridge preservation and bridge strengthening. So what I'm going to cover are a little bit of a historical perspective on the use of FRP materials, because they per se are not new technologies, anything that's been around probably 20 or 25 years. I mean, maybe in the grand scheme of things they're new, but I want to focus a little bit on some of the newer technologies and some of the advancements that have taken place, especially for bridge preservation. So let's, okay, so just a quick overview of what the state of our infrastructure, and you know, this should not be news to anyone in the room. Hopefully many of you are familiar with the report card from American Society of Civil Engineers. And you know, the good news is actually bridges are getting better, believe it or not. They used to be a C, and now they're up to a C+. So that's the good news, but the overall grade of our infrastructure is still a D+. And the, you know, the bigger news is that there's a lot of bridges out there, obviously. There's over 600,000 just on the bridge inventory. 1 out of 11 are still rated as structurally deficient. That's actually gotten a little bit better from the previous report cards that have been put out every couple of years. The other thing that's important to note is that our bridges are also getting older, and that's, you know, no secret there. I mean, 4 out of 10 bridges in the U.S. are over 50 years old. And when you think about when most of these bridges were built and designed, they were probably built with about a 50-year service life. So that's why it's important that we now just don't let these bridges just completely fall apart and take them down and then build new ones. If we can gain additional service life out of some of these structures and maybe get another 10, 15, 20 years with some of these newer technologies, and then I think what it allows us to do is to spend our money more wisely until funds become more available. And then, if you see the total infrastructure needs in the U.S. over the next 10 years is over $4.5 trillion. So again, even if, you know, we've been talking about the new infrastructure plan, which hopefully will turn an infrastructure bill, you know, even if it's at $1 to $1.5 trillion, that's still only about 25 to maybe 30% of what the actual needs are for upgrading our infrastructure. So it's important to keep in mind, you know, how much we actually need and how much money is being allocated for bridge repair. So why do we need to strengthen structures? Could be many reasons for upgrading our existing inventory. You can start things with insufficient reinforcement. The root of a lot of the problems that we have in the U.S. and really around the globe is damages from corrosion. De-icing salts, marine salt environment, marine environment in general, chemicals, caustic chemicals that are in the atmosphere. So that creates a lot of the problems, and from a lot of the presentations that we've seen earlier today, you can see some of the damages that can occur. Also, things like change in use. You know, again, when our interstate system was designed and built back in the 50s, the size of the vehicles was much smaller. The traffic volumes was much lighter. So now we're putting a tremendous strain on our infrastructure. And again, we have to be able to keep up with the demands. All types of damage can occur, whether it be structural, impact, fire. Lower right corner is the picture from the Northridge earthquake back in 1994 from a seismic event. Again, that's sort of beyond the scope of repair or strengthening at this point, but the point here again is if we can rehab and upgrade some of these structures before these catastrophic events occur, not only can we save structures, but oftentimes we can save lives as well. And then, you know, things like blast hardening, things we never really thought about 15 or 20 years ago, are now an important aspect in bridge repair and strengthening. And with all the hurricanes and the storms and the damages from Mother Nature, again, we can upgrade structures with the use of FRP materials. So let's talk a little bit about specifically FRP repairs, some of the advantages. Big thing with FRP is we can optimize the limited funds that we have. So when we have we can have some cost scheduling benefits. Some of the federal highway, mantra is to sort of get in, get out, and stay out. So get the repairs done in a timely manner and don't come back there in the future. This all leads to reduced maintenance cost. The fact that we're using lighter weight materials, some of the traditional materials for strengthening, we're using concrete, steel, all the materials that are used to design and build bridges. Now we're using much lighter weight materials for upgrading them, so it puts less of a strain on our infrastructure. The other big aspect of FRP materials is the fact that they are non-corrosive. So again, we don't have to worry about long-term maintenance. We know that these materials do not rust, they're inert, and they're essentially there for the life of the structure, again, leading to longer-term sustainable type performance. And again, the fact that we can get in and get out faster means that we can allow for less expensive repairs, and then what that creates are the ability to repair more structures when we have a fixed budget, which is always going to be the case. So this slide just kind of illustrates the comparison of some of the use of FRP materials with the conventional types of reinforcing steel or post-tensioning strands. Important to note, these material properties, at least for the carbon fiber and the glass fiber, are just the fiber properties, so it's not the cured laminate properties. But the point here is that we can use materials that have a much higher tensile capacity when compared with conventional steel, but also, allow us to sort of optimize the strength of these types of materials. Kind of a rule of thumb, it's not exactly the case, but, you can think, especially with carbon fiber, they're about, say, 4 to 5 times stronger than, say, conventional steel, but they're about 1/4 to 1/5 the weight. So that strength to weight ratio is really one of its biggest attributes in addition to the corrosion resistance. When we design with FRP, we have to also take into account that we're working with different types of materials. They don't have quite the ductility that steel does, so we have to make sure we impose strengthening limits on them to maintain a ductile nature of the overall structural member. Also make sure that we're working and designing to provide some type of secondary or supplemental reinforcement, so it's used in conjunction with the existing concrete and steel that's already in place, and also take into account any fire, life safety issues. Especially, this is more probably the case for occupied buildings, but certainly on bridges as well. We want to make sure that we're designing in accordance with local safety codes. And there are national design guidelines that are in place. American Concrete Institute has a Committee 440, has a number of documents that have been published for about the past almost 20 years now on the use of externally bonded FRP materials. And then Federal Highway and NCHRP has put together a number of documents, specifications and different documents for the bridge owners and for the specifier in order to create design documents. The FRP software, or different ways of designing, you can take the materials that are in the published guidelines, that, for instance, from ACI 440, and actually put it into design software packages. So these are available from a lot of the manufacturing companies that market and sell the materials. So a lot of these materials are available, again, from the various companies that are actively involved in supplying materials. So let's talk a little bit about the evolution of structural strengthening, because it has gone through a number of changes over time, and from when it was first done. If you think about strengthening existing structures, steel plates have been used for over 50 to 60 years. Actually, there's been case studies that go back to the 1950s, so almost 70 years ago, where steel plates were either epoxy bonded or bolted onto beams, slabs, even column jacketing, again for stiffening and upgrading existing structures. This was sort of replaced over time, but really in the early 1990s is when the use of carbon fiber and FRP materials first came to prominence, at least in terms of a commercial aspect. And here you can see some carbon fiber plates that were used, again, for flexural strengthening back in the early 1990s. Then glass fiber wraps were used for a lot of seismic strengthening, also in the early 1990s, and Caltrans is one of the early proponents of this for replacing steel jacketing, again for seismic upgrades. Some of the early systems were done with what's known as a wet layup process. I'll show you in a few seconds what we mean by a wet layup. And then carbon fiber as well. You know, there's different ways of manufacturing FRP materials. I didn't really get into the main differences between carbon and glass, but there are different material properties that carbon fiber and glass fiber have for different types of systems. But these have also been used more for structural type of applications, whether it be shear strengthening, flexural strengthening, as well as column wrapping. And then more recently, the advent of pre-saturated or pre-preg FRP fabrics were really just introduced for construction applications really less than about 2 to 3 years ago. These similar types of systems have been used in other industries for many, many years. In fact, the marine industry has been using them since the 1980s, and some other industries have actually going back even prior to that. So I'll get into sort of the differences between the wet layup and the pre-sat in a second. So again, if we look at what a wet layup process is, essentially what we have is a dry fabric and a wet resin, typically an epoxy resin, and then we combine them together to create a composite system or a composite fabric. So in this case, we're combining a glass fabric with an epoxy resin, and typically it's done either on a flat station where you're actually forcing the resin into the fibers, or in some cases we can actually use equipment that's sometimes referred to as an impregnator or saturator and sort of force the resin onto the fabric. So this is all done on site to create that composite laminate system between the FRP, between the epoxy and the fibers. The difference between that and what's known as a pre-preg or a pre-saturated system is that the pre-pregs are reinforced fabrics that have been pre-impregnated in the factory, sort of in the manufacturing environment. So again, these have been used in other situations. You can see in the aerospace has been using them for many years for constructing the fuselage and other parts of the airplanes. Military has been using these materials for many years. Again, the main difference or the advantage of a pre-saturated system is that it eliminates that step out in the field for wetting it out. It's all done in advance. Typically, the resin that's used is what's known as a B-stage epoxy, which is a partially cured resin. Okay, because what you don't want is you don't want the resin to start curing before you need it. It has to remain pliable, and then it has to cure in the shape that you want it to cure in. So what that typically is meant is you have to keep it somehow cool, either in refrigerated trucks, keep it refrigerated right before you install it, and then you have to put some type of heat to it to make it kick off and to cure. So that's why it's typically used in more of a controlled condition, like a manufacturing environment or places where they actually manufacture planes, where you have the room to put an oven or an autoclave. And that's really the main reason why these have not been used too extensively in infrastructure applications, because it's very cumbersome, obviously, to bring out heating equipment or autoclaves out on a bridge column. So that's why they have not been used quite often in bridge applications. But they have been used successfully in aerospace, wind energy, other industries since the 1970s. So if we look at the use of pre-saturated fabrics for civil engineering or bridge applications, now what we can put together is an improved quality control, something that's manufactured in an ISO 9001 facility under controlled conditions, optimized resin to fiber ratio. So again, we're not relying on the contractor to mix up so much resin and apply so much fabric. It's all done sort of in a controlled condition under optimized conditions. The fact that you can do this without having to make the contractor mix up the epoxies and actually do the saturation on site, it not only makes it a better quality system, but it also improves the productivity. They can do it a lot faster. The pre-saturated fabrics are much easier to cut because they're they get less fraying since they have the resin already built into them. They can also be air freighted. They're non-hazmat material. The difference between the B-stage epoxy that I mentioned earlier and the ones that are now used for bridge applications is a different resin type system. So in this case, what we're using is a moisture-cured resin that allows it also for use in wet or damp conditions. So it's, in order to prevent it from curing prematurely, it gets packaged and shipped in hermetically sealed pouches or foil packs to keep the moisture out of the package until you open it up. Once you open it up, it gets exposed to the ambient relative humidity, and that's when the curing process will actually start. Very similar to moisture-cured resins that are used for construction joint sealants and all types of waterproofing systems as well. And essentially what we end up with is something that can be done with reduced labor and also with a faster installation. So the moisture-cured urethane is the saturant. Again, no refrigerated or storage transit required, no equipment to heat it. It cures at ambient conditions, so you don't need it. Basically, it'll go anywhere from about 40 degrees Fahrenheit up to about 120 degrees Fahrenheit. So you have a very wide range of temperatures that it would work in. Repeatable strength due to the consistent resin to fiber ratio. Installations available, like I mentioned, even in very damp conditions or saturated concrete conditions. Oftentimes with epoxies, you want to wait until the concrete has dried out so you get a better bond. Since this is a moisture-cured system, it actually will bond very well even to damp concrete. Little to low VOCs, and low odor makes them user-friendly. And also the fact that this is the first factory saturated FRP system that's in use for concrete repair and strengthening. So here's the typical steps that take place in a wet layup system, and it's a very linear progression, multiple steps, and you really have to make sure the contractor, you know, they get trained and go through all these steps from providing the resin and mixing and saturating and cutting the fabrics, and I'm not going to go through everything, but the point here is there's a lot of steps that have to take place, and if you eliminate or if you kind of, you know, cheat on one step, that can compromise the entire system. So again, if we compare that to a pre-saturated system, what it allows us to do is sort of cut out about half of the installation steps. The biggest time saver is really the mixing of the epoxy resin and the actual saturation of the fibers. That's the part that probably consumes at least half of the installation time, even before you bring it out onto the column and actually start wrapping it. So I'm going to go through just a couple of case studies and just try to show you some examples of where these materials have been used over the last 3 years. This is an example of the RFK Bridge, which was formerly known as the TRIBOROUGH Bridge in New York City. So it's a series of 3 bridges that connect Manhattan, the Bronx, and Queens, but the landing spot for the 3 bridges is actually right in the middle on Randall's Island. There's been this complex opened back in 1936, so it's been around for over 80 years now, and there's been quite a bit of concrete deterioration, a lot of de-icing salts, corrosion damage that has taken place. So the purpose here was to do a lot of concrete repair and patching, and then also provide a FRP glass system for confinement. They didn't want to have to come back and you know, work on these patches again in the future. So this was not necessarily a strengthening application, but really more as a confinement for the patches. So here you see, originally, the first phase of this project actually used the wet layup system. So here's an example of the concrete being primed. The fabric, which has already been saturated, is being laid up on the underside of the girders, and then finally it gets coated. So this was the first phase. The second phase was done with a new contractor where they actually utilized the pre-saturated systems. And again, here you can see essentially just them opening up the foil, cutting it to length. After priming the concrete, you lay it right up onto the concrete. So here you see them working off a couple of scissor lifts. In this case, the work crew is really only 2 people because you don't need anyone, again, to mixing and saturating. So essentially you just need the guy cutting it to size and bring it up onto the lift and wrapping it around the, in this case, the column. And the right picture is where they actually, after they put the protective coating on for UV protection. 2 other projects were done. These were a little bit different. This is an I-15 bridge in Pocatello, Idaho. This one was a damage from an overheight truck, a high-load truck. Again, a lot of damage was done to some of the strands. And again, in this case, they are using a carbon fiber system because they had to restore some of the structural integrity of the material. The advantage of the pre-saturated system here is they had a very limited time to work with the materials. They didn't want to shut down the bridge for too long a period of time, so they can essentially get this done in probably about 6 to 8 hour total. The design for this was 3 layers of the FRP on the bottom, 2 layers as a U-wrap, and then 1 additional layer along the web. That was to restore the strength that was knocked out by the strands. And then a similar application on the I-40 bridge in Albuquerque, again, a high load piece of equipment struck the underside of the truck, the underside of the girder. In total, 6 girders were actually affected by this one. Here, the Albuquerque, the New Mexico DOT, wanted all this done nighttime construction, again, to minimize delays. And again, about 1,400 square feet of concrete was patched and then strengthened with the pre-saturated FRP materials. So the last one before I finish up is the National Park Service Storage Area Bridge in Washington, D.C. This is actually a small bridge, very just adjacent to the Lincoln Memorial. And again, you can see the location here. This underside of this bridge was used for a lot of storage by the National Park Service. Again, they were concerned here with the concrete that was very damp. Here you have a moisture meter to measure the moisture content in the concrete. Typically, if you're over about 4% moisture, that's when you don't want to use epoxies. You want to either dehumidify it or wait for it to dry out. In this case, they were able to get onto it because they had no moisture issues with the moisture-cured resin. Here you see the application of the primer applied onto the material, onto the concrete. Here's the FRP that was applied in the bags. The contractor is literally just cutting them into strips and then wrapping it around the column. Again, you can see just workforce on each column is only about 1 to 2 people because it's a very simple process, wrapping it and then just using some type of fiberglass rib roller to smooth it out. And then finally, some future work. As far as, since we have moisture-cured resins, we can also now look at the use of these materials for underwater or completely damp or even splash zone applications. So the moisture-cured urethane resin, we know it will cure in a high humidity and submerged conditions, also for damp or wet concrete repairs, and also for use in pile jacketing, which is another big application either on concrete or timber type piles. So in conclusion, our U.S. infrastructure is literally crumbling before our eyes in critical need of repair. Again, extending the service life of our existing bridges is one of the key elements of sustainable repairs. FRP composites have been used successfully on really thousands of projects around the globe for well over or close to, I would say, about 25 years in service life. And the fact that FRP composites are available in many shapes and functions allow us to repair just about any type of geometry that's out there. And the use of these new pre-saturated fabrics offer some significant advantages over the current wet layup systems, can reduce labor, gain efficiency, and save owners labor, time, and money.
First, what kind of surface prep prior to applying any of the materials do you do to concrete? And second, do you see local owners being able to use this with their own forces, or is this more a contractor specialty?
So as far as the surface prep, the HCI 440 guidelines goes into some detail on what's the adequate or the recommended surface prep. ICRI, which is the International Concrete Repair Institute, has what they refer to as surface profile tips. So generally you're looking for something that's like a CSP 2 to 3, which is almost like a rough sandpaper finish. You're trying to mechanically abrade the concrete, roughen it up, and get rid of any weak concrete that's on the surface, any paints, graffitis, things like that. You don't have to get more aggressive than that. If you were doing a concrete patch, you would probably need to expose some of the aggregate, but really you're just abrading the surface with some type of mechanical shot blast, sandblast, abrasive grinders. As far as the repairs for, I would say, yeah, on larger projects, obviously, you're going to probably work with specialty contractors that have been trained. But we have trained some of the maintenance crews on smaller bridges so that they can go out, whether it be for emergency type repair or maybe some spot repairs. So it's certainly something with the proper training can probably be done by a maintenance crew on a smaller scale basis.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.